Welcome everybody to the second iteration of the orientation meeting for the CompuCell workshop that's coming up at the beginning of August. This is going to be a very quick zoom through a number of possible things that you might like to do to prepare for the workshop, and also a little bit of a troubleshooting session to make sure that people don't get stuck at the beginning of the main workshop. The slide deck is available online in the student materials folder. We have the Zoom chat, and so if you have questions or comments, you need to be moved into a breakout room for individualized help. You can do that. We have a workshop Slack, which will be monitored, which you're welcome to use. I need to tell you that this session will be live streamed on YouTube and that the videos are going to be archived and made publicly available, so remember that. And one of the things we're going to be doing during this little workshop prequel is to make sure that you have a nanoHUB account, and if you're going to be installing CompuCell Desktop, that you would do that. So I'd encourage you to do that. And we always like to thank our funders for their generous support of this project. So I'm going to do a very, very brief welcome. And we're going to talk a little bit about course logistics, resources, and then I'll walk you through the main CompuCell tools. We'll actually build a little simulation together and run it. And then we'll talk a bit about some of the background material you might want to look at before the course starts. I want to say that we have about 150 people registered for this course. That's a lot. Of course, not everybody comes on a Zoom course, but it's going to be a big crowd. That's great. We're very happy about that. But if any of you happen to be experienced CompuCell users and would like to help mentor people who are less experienced, we'd love to have your assistance. And you could email tjseago@iu.edu if you want to volunteer. So as a welcome, I'd like to say that the kind of modeling we're talking about is focused on the issues of tissue organization. How do organisms develop? How do they maintain themselves? And how do they fail? And lately, we've also been using it quite a bit, and a large number of people have been using it to build models of infectious disease and immune response. And we can certainly talk about that in the main course. This tool also has been used in the context of developmental toxicology by the U.S. Environmental Protection Agency. And it's been used in bioengineering applications to do tissue engineering design. While biology has many, many length scales, and some of those scales can be included beyond the ones that we typically focus on, most of the models that we'll build in the course are going to include some concept of networks that control cell behaviors. Those could be metabolic networks, gene regulatory networks, or signaling networks, cells and their behaviors, and the extracellular environment and how cells move and adjust in that context. And so here we have a simulation of chick embryology, of the formation of the somites that are going to form the segmental vertebral structure of the chick. On the right, we have a set of subcellular signaling and gene regulatory network models that are oscillating. In the middle, we have an extracellular concentration of a morphogen, FGF8 in this case. And on the left, we see the cell differentiation and rearrangement that happens when cells read their internal clock, oscillator clock, and differentiate in response to that morphogen. And that would be a typical kind of simulation one might do. There are many others. That would be a typical kind of simulation that we might do, going from the subcellular regulatory level up to the tissue and organ level. One can do simulations where one has whole body representations, and one can take these cells and subdivide them and put in subcellular compartments that represent the nucleus, subcellular domains, apical domains in epithelial tissue, and things like this. But these are the ranges of simulation we're talking about. Course logistics. We're going to have links, which I posted already in the chat, for the Zoom for the Python Bootcamp. That's the Sunday before the course starts. The Zoom link for the main course and for the hackathon. I hope many of you will participate in the hackathon. Please take a minute to make sure that you can register successfully for these Zooms. There is a link for a document, a Google Doc, for the hackathon, where we're asking you to post your ideas. There's also a hackathon Slack channel. Let me see if I can post that into the chat here. The Google Doc here. And as part of the course, we're going to have 2 sessions to help people partner for the hackathon. And so we're going to ask that everyone who wants to be in the hackathon who has an idea, give us just one slide presenting their hackathon idea and upload it. And I put the link for that upload in the chat. Zoom logistics. I assume everybody who's here knows how to use Zoom. There's so many features in Zoom. Sometimes it's hard to keep track. Please feel free to use the yes, no, go slower, go faster, raise my hand, I need help buttons in Zoom. I'm going to use polling systematically throughout the workshop. You'll have a poll that's thrown up that says, how are you doing with the exercise? I'll show you that in a minute. And you can click yes when you're done with the exercise. Since you can't change your response, typically it's better to wait until you're done to say yes. But if it looks like we're going to move on without you, please click I need more time. And if you need help, say help. And if you're not going to do the exercise, please say I'm not doing the exercise, so we don't wind up waiting for people who decided not to do it. People, we have several of the instructors in the room. Myself, James Glazier, Indiana University, TJ Sigo, who's the lead developer of CompuCell, Gilberto Tomas, who's joining us from Brazil, and is a regular for 20 years in this course, teaching it. Giulio Belmonte, professor at North Carolina State University, who's going to be helping teach and is a very experienced CompuCell user. 2 graduate students, Giuliano and Josh. Jim Sluka, who's a senior scientist specializing in toxicology and drug dosing. And Bobby Matamanchi from University of Michigan, who's an expert in scientific education. So this is the team, potentially some additions or changes depending on the day, but that's the basic team. We're all available to do our best to support you when you need help. The course itself will consist of the same thing repeated for 5 consecutive days, actually 6 consecutive days, including the Python workshop. It will be broken up into 4 modules. Each module will be an hour-and-a-half long and will consist of about 1/3 to 1/2 of lecture and about 1/2 to 2/3 of in-person exercises. We'll try to make sure that we don't spend all of our time talking to you, although 1 or 2 of the sessions may be talkier than others. We're going to start every day, if possible, with a half an hour before things get officially going, where we have opportunity for conversation and troubleshooting. There'll be a break of 15 minutes between each module in the morning and the afternoon. Of course, if you're in different time zone, morning and afternoon may not be right for you. We'll have a half-hour lunch break, in quotation marks, in the middle of the day, and then a half an hour after the main session for informal discussion and more troubleshooting. And we'll repeat that throughout the course. The tentative course outline is day 0. The Sunday, August 1st, will be a Python tutorial refresher that will be taught by TJ Sigo. And then we will launch into a few examples, which I'll present, and some discussion of simple CompuCell simulations on day 1. Day 2 will focus on how cells move, a little bit of help organizing hackathon issues. and how to simulate chemical fields and the responses of cells to chemicals. Day 3, we'll talk about cell growth and division. We'll build a simple avascular tumor spheroid model. We'll build compartmental cells and talk about in more detail how cells move. Day 4, we'll talk about more advanced concepts, in particular, how to build epithelial models of epithelia and how cells link together and move relative to each other using filopodial extension. Those are methods that were developed by Giulio Belmonte. We may have another short hackathon organization. We'll talk a little bit about using the software to do things like parameter scan. And the last day will be devoted to putting subcellular control into these models using Tellurium, SPML, and our new MabBoss software integration. The schedule may change a little bit, but those are the basic topics. The hackathon will be on the weekend after, Saturday and Sunday. You have self-organizing teams. Please, if you want help finding partners for your teams, contact us, talk to us. We'll help you try to refine your ideas. Those hackathons will start with a quick set check-in for everybody at the beginning of the session and at noon. In the evening of the first day, we'll ask for very brief reports from each team. On the evening of the last day, we'll ask teams to have generated a small presentation of their results, and will be available to help people develop their results further after the hackathon. Over the years, many people have developed work that they eventually published starting in this kind of hackathon mechanism. So again, post your hackathon ideas to the Slack channel, put them into the Google Doc that's been shared. And again, so that we can do lightning talks on that second day, please, by the end of the first day, August 2nd, give us a single PowerPoint slide that we can integrate into the presentations for your ideas. Resources. So the main resources are going to be two places. The CompuCell website has manuals and other material, and we'll try to post most of the course material into the conference subdirectory on the website. That takes a little more time because you have to edit the HTML. So there also is a Google Course Drive, which I hope everybody has access to. Let me make sure that I post that now to everybody so that you have it. I'll put that in the chat. So that should give you the links for that. The Tellurium links are a very useful online material for doing subcellular modeling, for doing signaling and regulatory modeling. And there are also the quick reference guides. They're available both on the CompuCell website and in the class files, and I think they were all mailed to you as well. There's the Slack. If you have trouble getting into the Slack, please ask for help. And the quick reference guides, I will say, are very useful, and I would strongly recommend, if you can, printing them out because they're very helpful to have on your desk next to the computer so you don't have to keep shifting windows back and forth when you're programming. The main ones are a introduction to Python, a Python cheat sheet, which is very helpful and has almost everything you'd want about Python in it. Tellurium, which is the language we'll use primarily to do subcellular modeling, very simple language to describe chemical reactions and signaling. And that cheat sheet is very helpful. And then there's also the CompuCell reference guide, which has been relatively recently updated for CompuCell 4.2.4. And so with those together, you'll have on your desk not everything you need, but 95%, 98% of what you need to be able to do the things we'll do in the class. If people want to dig a little bit deeper, there is in that folder a copy of an article we wrote some years ago on the history and the mathematics and physics behind the modeling methodology. And that gets somewhat heavily into the physics of how CompuCell works. You don't have to know that to use it, but if you're interested in actually how the computations are done under the hood, that's the place to go. We also posted a recent article by a group in Canada that's not about multicellular modeling. It's about biological modeling very generally. It's not a perfect match to what we're doing, but if you're not familiar with the process of going from ideas in biology to mathematical and then computational models, it has some very good material in it, and I recommend reading it. It's a nice introduction to modeling. So now I'll move on to CC3D Tools. CompuCell consists of two main software tools: an editor where you write your model specifications called Twidit, and it's a specialized editor. It has all sorts of features that make model specification easier and helps you avoid the common mistakes that people would make. And then CC3D Player, which takes those model specifications and allows you to run them and interact with them. And so you're always going to be working with these two tools, one of which you use to build and work with the model specification, the other one in which you can execute the models. So with that, we're going to move on to installing and running CompuCell 3D. You can certainly free to run it in desktop, but the demonstrations and teaching we're going to do are mostly going to be done using the online nanoHUB version of CompuCell. That has some disadvantages and annoyances, but it has the advantage that everybody sees the same thing. Whereas if you're using Linux, Mac, or Windows, the user interface is going to be slightly different because of the windowing systems. Installing on Linux can be challenging. And so instead of taking your time worrying about the install, working with the web-based interface means that you don't have to install anything on your computer. So I'd like to get everybody up and running on nanoHUB. The first thing to do is to type in the link to nanoHUB, https://nanohub.org, and I'll put that link in the chat. And I'll also put the link in for the download for CompuCell. And I'd like people to follow along with me while we do this. And you'll see this. You'll see this is going to be sort of typical format that we're going to use for the class, which will be to have the slide deck on one side and the software running either desktop or online on the other side. And so I'd like to ask everybody to go to the nanoHUB page and log in. And so I'd like, I'll do our first poll, which is simply were you able to get to the nanoHUB page and establish a login. And so find nanoHUB. If anybody can't find nanoHUB, let me know. And then you go to menu and you hit, well, I'm actually already logged in, but you'd hit login. And then it'll ask you for your affiliation. If you're in an American university, you're probably there already. You don't have to be with an American institution. You can sign in with Google or LinkedIn, or you can create your own nanoHUB account. No matter where you are in the world, you ought to be able to get into nanoHUB. And so I want to make sure that everybody has access to that. People are saying they need a little bit more time. If anybody's having trouble with that, let us know and we'll do our best to walk you through it. I guess I can log myself out and log back in. So, log in. In my case, it knows that I'm at Indiana University, so I can sign in. And once it's got a cookie in your browser, it'll recognize you. You may have to re-credential every so often. If you leave a session open, it'll stale. But beyond that, it should be okay. Let's see how people are doing. Give people another minute or two to try that out. If you have gotten in already and you want to move ahead a little bit, you could go to the next step, which is to find your dashboard. Your dashboard is typically hidden when you first log in. If you come up to the top and hit menu and select dashboard, it will take you to your user page. And so you can try to find that. And you can do two things. You can either, once you're logged in, you can go back and click this link again, the one that points to CC3D base 4X, which will open that. Or you can go under, nanoHUB has all sorts of interesting software tools to play with. So it's not just CompuCell. You can also go to all tools and then start searching CompuCell 3D V4, and that will pull up the tool. Once you found the tool, we recommend you hit this little heart, which will bookmark it for you, and leave it on your desktop. And then to launch it, you hit this square box here, this window box on the right. Don't be shy if you need help with this. Feel free to raise your hand and let us know if there's anything we can do to help you get this working. Okay, so what I'd like people to do now is find CompuCell 3D V4, click this launch button, and it may take a little bit of time to launch, but you should see a blue box that looks like this on your screen. Depending on your settings, it may have done something different. It may have launched. It'll remember the last thing you ran. So in my case, it remembers what I ran before, so it's launching that. You may see something slightly different, but the key thing is simply to see that it launches. I want to make sure that everybody can get that running because we'll need it for everything we're going to do in the class. For the Python tutorial itself, I should add that we'll be using a different tool. It's also available on nanoHUB. It's called Tellurium. And so if you are interested in got CompuCell up and running, and while we're waiting for the other people to get their installation going, you can type in that search tool there, Tellurium, Tellurium, and you could bookmark that and put it up too. And it's going to launch a Jupyter Notebook installation for running Python tools. Somebody says that they need help. So if you need help, please either raise your hand or send a chat message, and I'll put you into a breakout room with one of the other instructors to get help. Okay, Steve, do you want me to move you to a breakout room? Would that be helpful?
Yes, please.
Okay, who would like, TJ, would you be willing to handle that?
Absolutely.
Okay. Does anybody else need help getting things going? Don't be shy about it. We're here to help. Okay, great. Everybody else is okay? Okay, so you should see something that looks like this on the right with CompuCell running. We're now going to talk a little bit about the desktop application. If you want to install CC3D on your desktop, I don't really recommend that unless you're running a Windows machine. It runs okay on Macs too, but the interface is a bit different. You go to the CompuCell website, go to most recent release. So you go to CompuCell website, click binaries, click most recent release. And in this case, we're going to be doing a Windows download. You click Windows here, and that will take you to SourceForge. And if you've told it that you have a Windows or Linux or a Mac machine, it should give you an option to do download latest version. And you should be able to do the install from there. As time has gone on, it has gotten more and more restricted. Both Windows and Macs have gotten more and more restrictive about what you can run. So the installer may ask you to override security on your computer. You'll need to say it's okay. It may ask you to run the installer as an administrator on your computer. It's okay. Remember that if you have trouble installing it on your local computer, you can always run it on the nanoHUB account without having to do anything locally for your computer. Once you've got it installed, my recommendation is that the easiest way to get CompuCell running is to search in your Finder, whether it's a Mac Finder or Windows Finder, for Twidit++ and open it. And that will get you to be more or less where we are with nanoHUB. Okay. So now I'm going to come back to the nanoHUB installation. If people need help getting CompuCell running desktop, please feel free to contact us. But again, I encourage you to stick with the nanoHUB version if you're just getting started. So I'd like to have everybody work today to write a very, very simple CompuCell simulation together to show you what it's like to write these things. And it shouldn't take more than about 10 minutes. And we're going to use the Twidit special feature called Wizard to create a simulation of cells growing and dividing and differentiating, which sounds like quite a bit. And we're going to use the nanoHUB tool to do it. The first thing we have to do is to learn how to use Twidit in nanoHUB. What we have running by default in nanoHUB is Player. And to switch to Twidit, you have two choices. You can either hit this button here, which shows a piece of paper and a pen. And if you hover over it, it'll say Start Twidit++. Or you can go to the File menu, pull that down, and click Start Twidit++. So I'd like everybody to do that. And what you should see is something that switches like this. And so let me make sure that people are able to get to work. Is anybody having a problem getting Twitted to launch? Okay. So once you have Twitted launched, one thing that you may find with nanoHUB, and it's one of these small annoyances that I mentioned, is that because of nanoHUB's interface, it doesn't always redraw the screen correctly. And so if you are left with an image screen like this, a window that isn't drawn properly, if you hover over the bottom right-hand corner, you'll get a resize arrow. And if you nudge that corner a little bit, it forces it to redraw the screen and clean it up. And I'm pretty sure we'll run into that. So remember that if your screen looks funny, pulling on that bottom right-hand corner will help clean things up. Okay. So we're now actually going to build a computer simulation together, and I'm going to make the window a little bit bigger while I'm at it so we can see better. And there is a button here called CC3D Project. We're going to pull that button down, that menu down, and we're going to click New CC3D Project. I want to make sure that everybody can do that. And it will pop something that says Multicell 3D Simulation Wizard. All right. Once you have Multicell CC3D Simulation Wizard running, you have to do two things. You're going to type the name of your simulation, and you can give it any name you like. So with a no space. No spaces or special characters in the file name. So let's call it cell sorting simulation. And you have to make sure that the directory it's going to try to write in is one that you can write in. On nanoHUB, you want to hit browse, and you will see computer, and then your username should be underneath. Make sure you select your username for choose. And you have now the name of the simulation, where it's going to go, and you hit next. If you were running a desktop, you would point to a directory that could be on your desktop or any directory that you have write access to in your Mac or your PC. Okay, let's make sure everybody can get that to work. If people need help, please speak up. Okay, everybody seems to have that running. So the first window we're going to see is general simulation properties. We're not going to play with that today. We're just going to accept the defaults that it gives us. And so we're going to hit next. And now the next window that we get is to list the cell types we're going to use in our simulation. And we're not going to be very creative. We'll call them cell 1 and hit add. And we're going to call it cell 2 and hit add. And that means we're going to have two kinds of cells in our simulation named cell 1 and 2. In reality, it might be stromal cells and cancer cells or some other kind of cells that we are interested in. But for our purposes, we'll just call it cell 1 and cell 2. And you have to hit add. You have to remember that. You can always hit back. So if you make a mistake, you can go back. But everybody should have something that lists the cell type specification, cell 1, cell 2. And now we hit next. The next option is to create chemical fields. We're not going to use any chemical fields in the simulation. So we hit next. And now we get a very important screen, which is cell properties and behaviors. And one thing we have to remember about an environment like CompuCell, in fact, any of these kinds of agent-based models, is that nothing happens or exists unless you assert it. So if you want a space in which for your simulation to run, you have to say that there's a space. That was in that first simulation block that we didn't touch. In this case, we've created 2 cell types, and we have to say what those cells do. And we're going to say that those cells stick to each other. That's the contact energy button here. We're going to say that those cells grow. That's the growth button here. We're going to say that those cells divide. That's the mitosis button here. And because the cells are going to grow and divide, they have to have a specified volume. And so we have to click this button that says volume local flex. So I want to make sure that everybody's able to do that, because this is defining actually the structure of the simulation. If anybody needs help with that, please speak up. Raise your hand. We'll do our best to help. Okay. Now we're going to hit next. It'll say configuration complete, finish, and you should see this. To view your simulation, you double click on the name of the simulation in this left-hand navigation pane, and that will open the simulation up. And you'll see that the simulation is composed of a number of files of different kinds. If you wanted to save the simulation, you can hit this down arrow here that says Save CC3D Project. You can hit the double floppy disk icon. Boy, is that obsolete, which is a Save All there. Or you can go up to CC3D Project, pull that down, and hit Save CC3D Project or Save CC3D Project As if you want to rename it. We're not going to need to do that right now, but that gives you the option of saving versions of your software and so on. And now we're going to run the simulation. And to run the simulation, depending on whether you're desktop or on nanoHUB, you have slightly different options. You can go into if you're in your desktop machine, this CC3D icon here would be blue. Clicking on that would launch the simulation in Player. In nanoHUB, Player is already running. And so what you want to do is hover over C cell sorting CC3D simulation, right click on it, and it will say Open in Player, and click Open in Player. And because there was another simulation, in my case, launched before, it'll ask me, do I want to stop that previous simulation? And I'll click yes. So let me make sure that everybody's able to get that to work. And once you've got done that, you have to click. You'll notice here now it says, now you have to switch to the other window, the Player window. And I can resize that here. And so this is now CompuCell Player. And it will have loaded the simulation that you've just asked it to load. And you'll want to resize it so that you can see what's going on. The usual arrow buttons work, so I can move this property box. I can change the size of it. I can change the size of the console. And I can always resize the whole window if there's an issue with the way things are working. And now we need to know how to control Player. Player has old-fashioned cassette tape type buttons on it. The first one with the arrow pointing to the right, is run. If I hit run, the simulation will run. And it didn't resize properly, so I'm going to have to click and resize it. The second button is step, that does one simulation step. The third button is pause, that will temporarily halt the execution and allow you to either single step it or resume execution. And the last button on the right is stop. If I hit stop, that will terminate the simulation. And if I now hit step again, it will restart the simulation from the beginning. And again, I may have to do some joggling to get my screen to behave properly. I'm actually, that's interesting. Better rerun that. Occasionally, Zoom will interact in an unfriendly way with nanoHUB. If all else fails, you can hit terminate and start over. But I'm going to try one more time here to make sure that this works. There we go. And now you should see something like this, and you can hit run, and you'll see that the cells will grow and divide. The colors that you get will be different depending on what your previous configuration of the simulation was. It remembers how you configured it the last time, and so you may have different colors on your screen from mine. If you're running it on a desktop machine, the latest version of CompuCell will also give you a key for the cell names and colors in the left here. That's not yet implemented on the online version. So let's see whether people were able to get that to work. So that's about what it takes to write a CompuCell simulation. Now, of course, in reality, you're going to have to go in and change the default settings that simulation gave you, but it does show that it's relatively quick to build a simulation and run it. Some people are saying they need more time. Does anybody need help with this? So if you tell us, we're happy to put you in a breakout room and have you help, give you help. Okay, somebody wants help. Can you raise your hand and I'll put you in a breakout room? Okay, hi, David. I'll put you in a breakout room. And TJ, TJ still here?
Yes, I'm here.
TJ, thank you. Can I ask you to help Ma and David.
Sure.
TJ, I'm not seeing you on the oh, I see. You can jump into the breakout room on your own, I think. Yes. Okay, great. Does anybody else need any help getting through that? Did it run for you? I hope so. Okay. So again, don't worry, we're going to spend a week doing this. So this was just to play for a few minutes today. I'd like to talk for just a second about what a CompuCell simulation looks like. So you'll have seen it and begin to think about what they look like. So we'll go back and we will look at the TwidIt file. And CompuCell simulations have two main components. There is a markup language called CC3D ML that specifies the static aspects of the simulation, what kinds of cells you have, how big the lattice that the cells live in is, those kind of things. And then there'll be a Python specification for dynamic aspects of the simulation. And both of those things are editable from TwidIt. We switch back to TwidIt using the tab function. So here I put the TwidIt tab forward. By clicking at the bottom of my nanoHUB box, I can switch back and forth between my two windows. And you should see this. On the right-hand side, there's a scroll bar that lets you scroll through your text. And to select the piece of the text that you want to edit, you can either click here at the top. We're going to look at the XML first. It says cell sorting simulation XML there. Or I can click here on the XML and double click in that left-hand navigation pane. Okay, so I want everybody to do that. And you should see something that looks like this. And now we'll very, very quickly walk through what CompuCell code looks like. At the very top of the simulation, it'll say CompuCell 3D, revision number. And there'll be a section called metadata that tells you something about debugging and of multi-threading, because CompuCell is intrinsically a parallel computing program. The next section called POTS tells you how big the physical lattice of the simulation is and how long the simulation is set up to run for. The next block here tells you the kinds of cells that you've defined. We defined two cell types, cell 1 and cell 2. And so that's asserting that those exist. You'll notice that these are called plugins, and plugins are the basic functions that are executed in C++ by CompuCell to do all of the hard work of the core code of the simulation. Chemical fields are also specified using plugins. The next thing that we have, and we have to scroll down a little bit to see it here, is a statement that the cells have a volume here. And then we see that we've specified that there is a contact energy between each pair of cell types. If we didn't specify that, when the cells touched each other, they wouldn't stick to each other. This tells us that the cells stick to each other. And lastly, we have a specification that instead of saying plugin says steppable. Steppables are things that are called less frequently than plugins. They're often implemented in Python. In fact, what we'll be seeing are Python steppables. This is a steppable called uniform initializer that's called once at the beginning of the simulation, and it draws a square or rectangle, and it fills it with cells. And it tells us how big we want the rectangle to be, whether we want the cells to be touching each other or have space between them, how big the cells should be, and what kinds of cells we want to fill in. And you could play easily on your own by changing the size of the box or the size of the cells and seeing what happens. If we look at our Python, and to do that, we can either click on Steppables up here or double click in the navigation bar here. And here we'll have our core Python. If the Python looks really unfamiliar, I recommend that you do a little background reading on Python or take our Python Bootcamp. We don't use a lot of Python, and we'll introduce it in the course itself, but the course moves pretty fast, and so it's helpful to have seen these things before. What we'll see after some boilerplate is something called the start function, which is called once at the beginning of the simulation. And now we're going to specify the behaviors of our cells. And we've said that the cells have a volume, but we haven't said how big they're going to be. And something that we're going to have to get used to, and we'll talk about a lot in the class, is that you can't actually specify the volume of a cell. You can specify a target volume for the cell and a compressibility for a cell. And the reason for this is actually pretty simple. Imagine that I had a balloon, and the balloon has some volume sitting on my table. And now I suppose I had 100 balloons, and I squeeze them into a box that's pretty small. The balloons will be compressed, and their actual volume will be smaller than the volume they'd have if they were sitting on your table. And so you can think here about the target volume being the volume that the cell would have if it weren't being pulled on or compressed. And that actual volume is what happens as the cell interacts with its environment. And so you'll be doing this a lot. This is called a specification by constraint. And it's something that we will work on clarifying for you as we go. The other thing to see is this, what's called an iterator. It's a loop for cell in self.cellList. And that's a fundamental concept in Python, which is iterating over a list. In a lot of languages, you iterate over integers or real numbers. You can do that in Python. But the fundamental concept in Python is that you do things to things. And in this case, we have an object called a cell that represents every cell in our simulation. And we want to do something, namely attach a volume, a target volume to all of those cells. And so that's the basic construct that we'll see. If we scroll down just a little bit, we see something called the step function. That's called once every time step in our simulation. And we see the same iterator for cell in self.cellList, cell.targetVolume plus equals 1. So what this does is every time step, the volume of the cell goes up by 1. And you could play with that growth rate if you wanted in your simulation. We want our cells to divide, and that takes a little bit more work. We scroll down here, and we create what's called a list. It's a Python object class, a container. Cells to divide. And that's an empty list. And we go through all of our cells and we say if the volume of the cell, the actual volume now, is bigger than 50, we add that cell to the list. And then we go through that list and we call a function self.divide cell random orientation that splits the cell. The last thing that we need to do in our simulation is say what happens when the cell divides, because we had started with one cell and we now have two cells. And we have a function called update attributes that's called when a cell divides. We have a concept of a parent cell and a daughter cell. And we assign half of the volume of the parent cell to the daughter cell. We copy or clone all of the other properties of the parent cell to the daughter cell, except that we have this little detail that says that if the parent cell was of type 1, we make it of type 2. Remember, we had cell 1 and cell 2 types. And if the parent was of type 2, we make the daughter cell type 1. So the two cell types oscillate when we divide. And that's the end of the computer simulation. That's all you needed to do that simulation. And again, if we run the simulation, it does something that's relatively complicated. It creates an initial condition I'm not sure why it's displaying average volume and surface. It's going to the wrong simulation. I'm not going to take the time to do that at the moment. So that was the end of the exploration of the tool. And of course, things always malfunction when you're doing a demonstration. So I hope they didn't malfunction for you. I want to talk a little bit about background knowledge and reading that you could do. People come to this course with all sorts of backgrounds. We've had everything from high school students to emeritus professors take it, everything from pure mathematicians to surgeons. And so each person has different background. You need to know a lot of different things, and unless you've done simulations of this kind before, it's unlikely that you've had experience with everything that you need. So one of the things you need is some basic biology, in particular cell biology and tissue biology, developmental biology. What are cells? What do they do? How do they create forces? How are tissues constructed? What's the difference between a mesenchymal and epithelial tissue? What's cell polarity? If those concepts are familiar to you, great. If those concepts aren't familiar to you, don't worry, but you might want to do a little bit of reading at the level of Wikipedia about what those concepts are. Another thing you might want to think about is how cells are controlled. What are signaling, metabolic, and regulatory networks, and how do they work? And a little bit about how you might represent those, both in drawings and mathematically. Those are things you might want to think about biologically. The mathematics we'll use, we'll try to minimize it. The underlying mathematics for CompuCell is relatively sophisticated, but for our purposes, we don't need very much. If you want to be able to understand how energies work and constraints work, you need to know what summation notation looks like. It's helpful to know what first order ordinary differential equations are if you're doing rate laws, how things change in time, and how those are represented mathematically. And Herbert Sauer is going to be teaching a course on this next week, where he spends a whole week on this topic. The only partial differential equation we'll use is the diffusion equation. If you've never worked with the diffusion equation, it's worth looking up in Wikipedia how the diffusion equation works. We'll use a few dynamical systems concepts of stability and fixed points, but we won't use it very extensively. The idea of sensitivity analysis, what happens when you change parameters, and the idea of stochastic rates. These are stochastic models where things happen with probabilities, and so it's useful to have that idea. For biophysics, ideal gas law and springs and constraints are very useful concepts. Diffusion is a useful concept, and if you're interested in how the back end of things works, there's some statistical mechanics that would be useful, but not essential. For Python, you've seen most of the Python concepts we'll need: loops, conditionals, object types, classes, dictionaries. And we'll talk about those in the Python Bootcamp. All of those ideas will be presented when we introduce them the first time. But again, if they're unfamiliar, it's helpful to have seen them once before you have to dig in. If you've never built models, conceptualizing models can be challenging. You want to think about what it is you want to model and why. And that's not a trivial problem. And in particular, how you map biological real world concepts onto mathematical and computer concepts takes some getting used to. And so it's probably worth reading that little article that I suggested and to think about that a bit as well. Again, we'll practice this a lot during the week, but it does take some getting used to. If you want to fill in background for Python, there's this great Rosalind online Python tutorial. There's a good textbook that we've got a path to here. For network modeling, Tellurium has great demos in the Read the Docs. There's a good textbook by Herbert Sauro. There's a wonderful classic introductory mathematical biology textbook called Essential Mathematical Biology that I recommend. For biology, I recommend old editions of Gilbert's Developmental Biology. The new ones have a lot of molecular detail you don't need, and they're expensive. You can buy a 20-year-old version for $1, $2 online, and it has everything you need and it's easier to read. For biophysics, Phil Nelson's Physical Models of Living Systems is a good elementary introduction. If you know some physics and want to dig into the details, there's a beautiful book by Phillips, Physical Biology of the Cell, that I recommend a lot. And depending on where you want to go in terms of model conceptualization, there's a very elementary but beautiful book by Gerli and Lund called Scientific Models, not specifically about biology. The 10 Simple Rules paper that I posted. And I also posted a partial paper of mine that never gets published called A Template for Model Development, Workflows in the Readings Resources that I'd recommend. And if you find anything that you find is useful in helping you on any of these topics that you'd like to share with the other people in the class, we'd be very grateful. We're always looking for good introductory material that helps teach these ideas. So to prepare, make sure you can get CompuCell to work, either locally on nanoHUB. Play around with loading, editing, and saving CompuCell simulations with Twit. You might want to try to run some of the built-in CompuCell demos. There's some nice ones. Recommend CompuCell Cell Python tutorial, stepables based mitosis, angiogenesis, and delta notch are great demos. The demos are not organized in the most logical way, so you may have to do some poking around. Let me show you how the demos look in Player. Try to get that one again. Let's launch CompuCell again. Okay, if I go to File and I do Open Simulation File, I will see CompuCell demos. I can click there and I'll have a whole host of possible demos that I can run. As I mentioned, the one problem with running these demos is that the names and the file structures aren't so obvious, so I encourage you to explore and see what happens. Encourage you to bone up on any areas that you don't feel comfortable with, you want some background on. Contact us if there's anything that you need. Wikipedia level familiarity is fine. You don't have to be an expert in any area, but you do have to know a little bit about a lot of things. And if you're interested in participating in the hackathon and you have a project you want to do, you want to think about a project, please do post that in the Slack and the Google Doc and send us a one-slide mini summary of your ideas so that we can do some teaming together on Tuesday of the week of the presentation. So that was the end of my presentation for today. And I'm open to questions or comments. We can help you out now. We'd be glad to do it. Does anybody have any comments or questions they want to address now before we break? No? Last chance for live discussion before we break. No? Okay, well, thank you very much. I look forward to seeing you in 2 weeks. Please feel free to contact us if there are any issues you want to address before then. And I thank the instructors for joining us and helping out. And I look forward again to working with you in the course. With that, I'll call the meeting to a close, and I'll see you in 2 weeks. Thanks again.